Section 3.1, the subspace topology. Definition 3.1. Let X be a topological space and let Y be a subset of X. Define T sub Y to be the set of all intersections of open sets in X with this subset Y. Okay. This is called the subspace topology on the subset Y, and with this topology, Y is called the subspace of X. Okay, so it was just a subset, but once we define the subspace topology on it, then we can call it a subspace, sort of a sub-topological space of X. Now we're going to say that subset V in Y is open in Y if V is an open set in the subspace topology on Y. Just sort of an abbreviation. So here's the picture. We have topological space X, the subset Y, and then to get an open set in the subspace topology on Y, we want to take an open set U in X, and then just intersect it with Y to get this little intersection here, which will be open in Y. Alright, so that gives us all open sets in the subspace topology. Now, what if we want to work with bases instead? Theorem 3.5 says that if we let X be a topological space and take just a basis B for this topology on X, and then we take our subset Y of X, and we intersect all the basis elements B from the topology on X with this subset Y, that gives us a basis for the subspace topology on Y. Okay. So we can either intersect all open sets with Y to get all open sets in the subspace topology on Y, or we can just intersect the basis elements for the subspace on X with Y to get a basis for the subspace topology on Y. A couple options. Well, let's try to apply this in exercise 3.1. Let X be a set of all ordered pairs X0 and R2, which is basically just the x-axis in the plane. Describe the topology that X inherits as a subspace of R2 with the standard topology. Okay, so we're taking the standard topology on R2, trying to figure out what's the subspace topology that induces on the x-axis. And, well, we have to, well, let's use the basis sort of characterization here in theorem 3.5. So we want to take a basis for R2 in the standard topology. And one option we have is to take the collection of all open rectangles in R2. Right? Open balls would work just as well, but open rectangles would be more convenient for what we're going to do. Now, according to the theorem, to find a basis for, well, Y, which in our case is this X, the x-axis, we're supposed to take all these basis elements, all these open rectangles, and we're supposed to intersect them with our subset X, okay, with the x-axis. And so there are some different positions you could put that open rectangle in. But if it sort of has the x-axis running through the middle of it, then the intersection with the x-axis is going to be sort of an open interval on that x-axis. Okay? Whereas if the open rectangle just sort of barely touches the x-axis or is above it or below it completely, then the intersection is going to be the empty set. All right. So let's write that down. By theorem 3.5, we have B sub X in our case, which by definition is B intersect X for all B in this basis B. Well, it's going to be either the empty set, right, or it's going to be one of these sort of intervals in the x-axis, which we could write as interval from A to B in the first factor times 0, right? The y-coordinates of all those points have to be 0. And that's a subset of R2. And for that to make sense, we need A less than B. Good. So by the theorem, this is a basis for the subspace topology on our x-axis. Okay. Now, if you look at that basis, we can get rid of the empty set because remember, when you look for all the open sets of the topology, you're going to take arbitrary unions of base elements, and you can always take sort of the union of nothing, which will give you the empty set. Okay. So let's say we can drop the empty set to obtain a basis. Well, it's just going to be what we had up here. Okay. So that's our basis for the subspace topology on X. Now that's a pretty good description of it, but maybe we could also ask, what are all the open sets? Right? What do we get by taking arbitrary unions of these sort of intervals in the x-axis? Well, it's probably clear if you just try to visualize it. Right? An open set in X with the subspace topology from R2 is a union of these basis elements. Right? And that union has the form, well, it's going to be U times 0, where U, a subset of R, is open in the standard topology on R. Okay. The reason is, if you take a union of a bunch of these, it's basically the same thing as taking the union of just these intervals in the first factor, which will give you an open set U in the standard topology on R, and then taking that times 0. Okay, so you get exactly U times 0. So we found a basis for our subspace topology, and in fact we've described all of the open sets in the topology. Basically end up with the standard topology on R, but then keeping 0 in that second coordinate. Okay, so that should do it.